Hey guys, Mr. Herc here, and welcome to another lesson of AP Precalc. This is lesson 1.11. Let's get right into it. So here's a bell ringer for day one. This is a 2-day lesson. We know that a rational function will have a whole at x equals 1. Remember that linear factor is x minus 1. And a whole is either equally heavy or top heavy, and we want to see which one of these rational functions could be that function m. Right? So for A, if we take a look, we see it in the numerator, but it's not in the denominator, and it has to be in the denominator to make it a whole or a vertical asymptote. So we can eliminate A. B, that factor is bottom heavy. Same with C, right? Because it's either a greater multiplicity in the denominator than the numerator, or a greater multiplicity in the denominator because it's not seen in the numerator. So D should be our answer, where here the multiplicity is greater in the numerator than the denominator. So D is our correct answer there. Now, if you remember from the last few classes, a rational function is just two polynomials on top of each other. Take that denominator polynomial, and if there's a value for which that denominator polynomial is equal to 0, then at that value, that function will have either a vertical asymptote or a whole where the denominator is equal to 0. So let's try, with everything we know about wholes and domains and vertical asymptotes, let's try example 1 together. So here, this is x squared minus 4. Write an equation in factored form, and then find any wholes or vertical asymptotes. So we're given this to us in standard form, so we need it in factored form. So we're going to factor this into x plus 2 and then x minus 2 all over x plus 2, x plus 5. This would be this in factored form, so I'll just translate this over here. Once we have this, we know that there should be a whole at the equally heavy factor at x equals negative 2. We also know there's going to be a vertical asymptote at that bottom heavy factor at x equals negative 5. Find the domain. The domain is simply all real numbers except wherever the denominator is equal to 0. So x equals negative 2, comma negative 5. All right, example 3. Pause the video now. Try this one on your own because I'm about to go over the answers. Write this equation in factored form. We can factor that numerator into x minus 4, x plus 3. We can also factor the denominator by factoring out an x to start with, and then we have x plus 5, x minus 4. Find any zeros. This is just where is the numerator equal to 0 where the denominator isn't. So x equals negative 3 should be our only 0. Find a whole. The only equally heavy factor is at x equals positive 4. And then vertical asymptotes, there should be 2 at x equals 0, x equals negative 5 there. Horizontal asymptotes, this is dealing with end behavior. So we want to look at our standard form, which this is bottom heavy. So we're going to have a horizontal asymptote at y equals 0. And then find the domain. This is all real numbers except x equals 0, negative 5, positive 4. And that is example 3 there. All right, so we also talked about slant asymptotes when we were talking about end behavior. We never talked about, though, how to find it. And so this is what it looks like here. Let's have an example of the function k of x, which is shown on this graph here. If we factor it right, you have a whole at x equals 2. You have a vertical asymptote at x equals negative 1. And then you have two zeros at 0 and negative 2 there. And that should be the two zeros there. So 0 and negative 2. So that's what the graph looks like. That's everything that we've identified so far. But if we take a look at the end behavior, it also has a slant asymptote, which we've seen graphically before, which basically means it's going to approach this line, whatever this linear line is, but never touch it. And that is what a slant asymptote is. And so to find the slant asymptote, you can use long division with polynomials, and I'm going to show you how to do that to find the slant asymptote of this function. So pretty much, let's go over how to do long division just with actual numbers. So if we're doing 676 divided by 21, we want to see how many times does 21 go into 676 just by itself, which it doesn't. So how many times does 21 go into 67? This is 3 at a minimum without going over. So this should be 21 times 3 is 63, and then subtract 0, 4, and then 6. How many times does 21 go into 46? This should be 2. 21 times 2 is 42. Subtract this is 4, and that is our remainder. 32 remainder 4. So 32 is our quotient, our remainder is 4, and then our answer should be 32R4 there. We're going to do that same process, but with polynomials and different terms. And so let's try this equation here. So we have 6x squared plus 7x plus 6 all over 2x plus 1. So we want to ask ourselves, how many times does 2x go into 6x squared? And the answer is at least 3x, right? And the way we get this is by doing 6x squared over 2x and simplifying. So those cancel out to 3, that cancels out to x, so 3x is our answer. Once we get this, we're going to subtract, or we're going to take 3x and multiply it by each term here. So 2x times 3x is 6x squared, and then 1 times 3x is just plus 3x. Then we want to subtract everything, so 6x minus 6x is nothing. You should always get nothing, so that's a good litmus check to make sure you're on the right track. Then we have 7x minus, so distribute 3x. 7x minus 3x is just 4x. So that's our answer, and then pull down the 6. Here, how many times can 2x go into 4x? And so this should just be 2. So 3x plus 2, and then multiplying this out, you get 4x plus 2, and then there you should get your remainder of 4. 6 minus 2 is 4, and then our quotient should be 3x plus 2. And so our answer is going to be 3x plus 2, remainder of 4. And so how do we know what our slant asymptote is? It's going to be whatever you get when you divide this by this. All right, so if our rational function was 6x squared plus 7x plus 6 over 2x plus 1, here we see the degree of the numerator is 1 more than the degree of the denominator, so we know there will at least be a slant asymptote from what we've learned in the past. And the slant asymptote is that line y equals 3x plus 2, where if we kind of graph that, the function may go maybe like this and then like that or something like that, right? So let's try another example. We have x squared minus 1 over x plus 7. Use long division to find the slant asymptote. So here we have x squared, and now what I like to do is add in a plus or minus 0x here as a space filler so that I don't get confused, keeping my terms in order. Divided by x plus 7. How many times can x go into x squared? Simplifying this, it's just x. Multiply this to get x squared plus 7x. 0x minus 7x is negative 7x. So here, how many times can negative 7 or x go into negative 7x? This just becomes negative 7. This becomes then pulling down the negative 1 minus negative 7x minus 49. And so this should be negative 7x plus 7x, which is 0. And then negative 1 plus 49 should be 48. So we should get x minus 7 and then remainder 48 over 48 should be your remainder. But here we don't actually care about our remainder. So actually when you're doing these steps, once you get to the -7 part, right? So like you almost don't need to do any of this work right here or find the remainder because we're only looking for our slant asymptote, which once you get the equation of a linear line, that's it. You're done. And it will be typically in the form of y equals mx plus b, slope-intercept form. So in this case, y equals 1x minus 7 is our equation there. All right. Let's try example 5. Pause the video now. Try it on your own because I'm about to go over the answer. So here we want to do long division again. So 6x squared plus x plus 5 all over 2x plus 1. How many times can 2x go into 6x squared? This is going to be 3x. Multiply this out, so minus 3 or 6x squared, and then 3x plus 1 is just 3x. Now we have x minus 3x, which is going to be minus 2x. Pull down that plus 5, and then how many times can 2x go into negative 2x? That's negative 1. And so we have this, we're done. This is our slant asymptote, 3x minus 1. All right, number 6, find the equations of the asymptotes of the graph of g of x. So first let's find it in factored form. So if we factor the top, you should get x, and then x plus 6, x minus 2, all over x plus 6, x plus 1. That should be right in factored form, so let me write that there. X plus 6, x minus 2, x plus 6, x plus 1. Vertical asymptotes, that's going to be wherever you have bottom-heavy factors. That's going to be at x equals negative 1. Horizontal asymptotes, that is going to occur at end behavior. If we take a look at our end behavior, this is going to have no horizontal asymptotes because it's top-heavy, so I'll write none. Slant asymptotes this will have, so let's do that long division. And I'm just going to add in that plus 0 just in case. And then x squared plus 7x plus 6. I would do x cubed over x squared, which is just x. Multiply this out, so x cubed plus 7x squared plus 6x. Subtracting it, 4x squared minus 7x squared is minus 3x squared. Negative 12x minus 6x minus 18x. And then if you want, plus 0. Now do negative 3x squared over x squared, which is negative 3. And that is your slant asymptote, y equals x minus 3 there. All right, so let's try example 7. Here we have a interesting fraction, or interesting rational function. We have one where we are given the numerator in factored form, but the denominator in standard form, and we are actually going to want to convert it to both forms now. And so let's take a look. Let's convert it to factored form first, and then we'll convert it to standard second. So factored, the numerator is kind of already good. You can leave that as is. All over, this should just be x minus 1 squared, where x minus 1 times x minus 1. Standard form, here you remember can drop these when converting to standard form because we're only looking for the leading term. So 2x cubed over x squared is our standard form. Taking a look at our factored form, we have from this only one x value that gives us a 0 in the denominator. So this should have one vertical asymptote because this is a bottom-heavy factor. So, and then this should also have no holes. So both are very important. So we can eliminate anything that says it has a hole. So A and C are gone. and then it does have a 1 vertical asymptote, so you could eliminate B, and you know D is the vertical, or D is the correct answer. It has 1 vertical asymptote. And here we see the degree is 1 more than the degree in the denominator, which means it should have 1 slant asymptote, no holes, and 1 vertical asymptote as well. All right, so now we're on day 2. This is 1.11b, and today we're going to be talking about Pascal's triangle and the binomial theorem. So here's the bell ringer for today. We want to find the slant asymptote if we had a rational function x squared minus 6x plus 7 all over x minus 2. So pause the video now if you haven't done it yet, because I am about to go over the answer. All right, so what we want to do here is just do long division. How many times can x go into x squared? Just put them on top of each other and simplify. So this becomes x. Now multiply both terms by x, so you get x squared minus 2x. X squared minus x squared is nothing. Negative 6x minus negative 2x is negative 6x plus 2x, which is minus 4x. And then how many times can x go into negative 4x? This should just be negative 4. And we're done here. So x minus 4 should be our slant asymptote. So B is the correct answer there. Now today we're going to be talking about Pascal's triangle and the binomial theorem. So expanding expressions in the form of like x plus 3 to the power of 6 or 7 or 8 can be really tedious, right? Let's try, just to show you how painful this could be, let's try x plus 3 squared, right? This is pretty easy to FOIL out. This should be x squared plus 6x plus 9, right? Nothing too terrible there. However, let's try it cubed. So basically this would be x plus 3 times x plus 3 squared, which if we FOIL this whole thing out, this is x cubed plus 6x squared plus 9x plus 3x squared plus 18x plus 27, which we can simplify to x cubed plus 9x squared plus 27x plus 27, combining like terms. And that was like a little hard, right? Imagine if we wanted to do it to the 7th power. That would take forever, you would think. But not after today, because I'm going to teach you a shortcut to do this, which you'll definitely need for the AP exam. And this is called binomial theorem. And basically, there's a lot of steps to expand any binomial. A binomial meaning like x minus 3 to the power of 8 or something like that. All right? So I'm going to work through an example. There's 8 steps. We'll go through them step by step, showing you everything you need to know along the way. So the first one is how to find this. You want to draw Pascal's triangle. And what Pascal's triangle is start with 1, 1, 1, and then 1's going down the sides, right? And so that's how you would form it. And pretty much each number is made up by summing the 2 numbers on top of it. So 1 plus 2 is 3, right? 1 plus 1 is 2. Like here, 20 plus 15 is 35. So 1, 1, 1, 2, 1. There should be 1, 3, 3, 1 on the side. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, right? And so that's important. The other thing that you will need to do is notice that this first row is going to be row 0, right? So pay attention to that. Very important. Will mess you all up if you do not get this correct. So that first row is row 0. The problem we're trying is 2x minus 3 to the power of 4. We're trying to expand that out there. All right, so step 1 was draw out Pascal's triangle. Step 2 is just identifying your a, b, and n term. So remember, this is our polynomial that we are FOILing out, but this is going to be in the form of a plus b to the power of n. So for this example right here, our a should be 2x, right? Make sure you include that x if it's part of the a term. Our b is going to be -3 because it's a plus b. So here this should be plus -3. Make sure you include the negative sign, and then our n is just 4, and that's just simply whatever this is to the power of. Right? So now that we have our a, b, and n term, we want to look at our Pascal's triangle that we wrote out, or will write out, and write out the coefficients. So remember, very important, the first row is row 0. Don't get this confused. And then once you have your numbers, you are looking for your n term. So here n equals 4. And so what row do we use? We want to use row n, or in this case, row 4, which is 1, 4, 6, 4, 1. So start on your paper with the numbers 1, 4, 6, 4, 1 kind of spread out and in that order. That's what you're going to do with this step. Once we do that, just add pluses before each term. So very simple there. Step 5, now we need to add in our a term, going from left to right and decreasing by a power of 1. So we know from a, b, and n, right, our n is 4 and our a is 2x. So we have 1, 4, 6, 4, 1. And so we want to start that first number and multiply it by a to the power of n. So a to the 4th, then a cubed, and remember we have pluses, a squared, a to the 1st, and then this is just a to the power of 0, which we know anything to the power of 0 is 1, right? So this becomes 2x to the 4th, 2x to the 3rd, 2x squared, 2x, and then we can almost erase that entirely. So let's do that now. And then there. All right. Make sure that the exponent goes on the outside, right? We want to do 2x to the 4th, not that. Those are very different because this, you're also taking the 2 to the 4th power times x to the 4th power, which is what we want to do, 16 times x to the 4th, not just 2x to the 4th, all right? So make sure your coefficients get a little bit of love too, right? Distribute that exponent to them as well. Right? Step 6, write in your b terms. This time we're going from right to left. And so here we started with a to the 4 and went down. Now on the other side, with that 1, we're starting b to the 4th, and we're decreasing by a power of 1 each time. Remember, this is b to the 0, which is always just 1. Plug in b equals, in this case, right, you identified b as -3, so plug that in. And then remember, this is -3 to the power of 4 in parentheses. This is not the same as -3 to the 4th. And this is what people will put in their calculator, which is wrong, because this is equal to -81, where you do this first and then just add a negative sign to it. But what we want to do is this, which gets you positive 81. And that's what we're looking for here. So make sure you just have parentheses around each a and each b, and then raise it to a power. All right, now simplify. So this is what we should get when you plug in everything. We haven't simplified anything yet. 2x to the 4th, remember, is going to be 2 to the 4th times x to the 4th, which is just 16x to the 4th. Do that for every other thing, right? So do it for your a terms first. Then I would recommend do it for your b terms, and then combine like terms if you can. There's no promises, and so this one is one where you cannot combine. So there's really no step there. All right, now you're done, right? You FOIL it out. You had that long, you had 2x minus 3 to the 4th. That would have taken forever to FOIL out, but now you just got it done in a matter of minutes, and now you know how to do it for any other binomial in the future. So let's try example 8. Use Pascal's triangle to expand x plus 2 to the fifth. So this, first thing I want to do is draw out Pascal's triangle. Right? So row 0, row 1, row 2, row 3, row 4. This is row 5. And then let's label everything. So A here is x, B is 2, and N is going to be 5, right? Our A plus B to the power of N. Once we have this, this is a nice one for us. Let's take our row 5 and throw our coefficients down. So we have 1, we have 5, we have 10, 10, 5, and 1. And now let's start a to the fifth, a to the fourth, a cubed, a squared, a. And then we have b to the fifth, b to the fourth, b cubed, b squared, and b. And now substitute a in for x. So this just becomes x to the fifth plus 5 times x to the fourth times b, which is 2. So this is going to be x to the fifth plus 10x to the fourth plus 10 times x cubed times 25. So this should be plus 250 x cubed plus 10 times x squared times 2 cubed, which is plus 80 x squared. Then we have plus 5 times x times b to the power of 4. So 2 to the fourth, which is 64 times 5. So this is plus, or no, 16, geez. 2 to the fourth is 16 times 5. So 16 times 5 should be 80, so plus 80x. And then this should be plus 2 to the power of 5 is just 32. And so this should be the equation for example 8 right here. All right. So now that we have all that done, you could be asked a question either like this, just to expand it out, or what is the coefficient on the term containing x cubed when it's all expanded? And that is going to be where you expand it, and you're basically just looking for the number 250. All right. So that should be it. If you have any other questions, please come see me in office hours, and I will